let's learn how to use inverse trigonometric functions in applications. The main purpose of inverse trig functions is to find the angle at which a sine, cosine, tangent, or ratio occurs. So one of the applications is finding exact values of the trig functions. You start off by letting the angle equal the inverse sine, in this case, of x. And then you're going to rewrite that as sine of theta equals x. And to find exact values, you're going to use exact values from the special angle ratios that you know to find the value of theta in the domain that satisfies the equation. In this case, negative pi over 2 to pi over 2, the domain of the sine. And again, you need to know those exact values for the sine and cosine and tangent. So finding the exact value of sine inverse of 1/2 involves, first of all, rewriting it. Theta equals sine inverse of 1/2. So we're going to rewrite that in terms of sine. Sine of theta equals 1/2. And we're going to answer that question. If sine of theta equals 1/2, what's the angle that gives me that? Well, the sine of pi over 6 is 1/2. So theta is equal to pi over 6. So again, the inverse sine of 1/2 is going to be pi over 6. Same thing applies for the inverse cosine function. And the only difference really between the sine and the cosine inverses is that we have a restricted domain for the sine function that's negative pi over 2 to pi over 2. The restricted domain for the cosine function is going to be from 0 to pi. You need to know those critical values of cosine theta at the special angles. To find the exact value of the inverse cosine of negative square root of 3 over 2, we're going to let theta equal the inverse cosine of x. Therefore, theta equals the inverse cosine of negative square root of 3 over 2. So we got to find the angle theta that's in that restricted domain between 0 and pi, whose cosine equals negative square root of 3 over 2. So we're going to rewrite theta equals inverse cosine x as cosine theta equals x. So that gives you cosine theta equals the negative square root of 3 over 2. And we know what angle has a cosine of negative square root of 3 over 2? 5 pi over 6. The only angle in that interval that satisfies the value that the cosine of the angle equals the negative square root of 3 over 2 is 5 pi over 6. Same basic rules apply for the tangent. The tangent's restricted domain is between negative pi over 2 and pi over 2. It's important to know the tangent values as well. And you can also get those by knowing the sine and cosine values at that given angle. So let's find the exact value of the inverse tangent of the square root of 3. First thing we're going to do, we're going to let theta equal the inverse tangent of x. In this case, the inverse tangent of square root of 3. We're going to rewrite that as theta equals the inverse tangent of x as tangent theta equals x. So therefore, tangent theta equals square root of 3. Now we're going to use that exact value to find the value of theta within the restricted domain that satisfies tan theta equals square root of 3. And that value is pi over 3. Pi over 3, the tangent is square root of 3. And that's because the sine is square root of 3 over 2 and the cosine is 1/2. Sometimes we're going to have composite functions. For example, we're going to compose a function that includes the sine and the inverse sine together. Since a function and its inverse kind of cancel each other out because it takes input, turns it into output, and then we turn it back into input, or vice versa. When you see compositions of functions that involve a function and its inverse, they're going to cancel each other out, and you're going to wind up with exactly what's in the input. For example, if we have the sine of the inverse sine of x, the answer is going to be x, because what happens is we take that value of x, we find its inverse sine, and then we take the sine of that. In the end, we wind up with the original. And that works either way. Now, you do have to be careful. The x does have to be in the domain, the restricted domain. If it's not, you have to modify that, and we'll look at that in a minute. The same thing applies to cosine. If you have composite functions that involve cosine only and cosine inverse, they're basically going to cancel each other out and wind up with the original input, provided it's in that restricted domain. Same thing applies to tangent. If we have a composite function of a tangent and a tangent inverse, regardless of the order, it's going to wind up with the original value, provided that it's in that restricted domain. Let's look at an example. The inverse sine of the sine of negative pi over 2. Now, you could solve this problem by finding out what's the sine of negative pi over 2, and then finding the inverse sine of that value. You could absolutely do that. Faster way is just to know that the inverse sine and the sine essentially cancel each other out, and we wind up with the original input of negative pi over 2. And negative pi over 2 is in the restricted domain of the inverse sine function, so it's okay, and that's our answer. Now here's a case where we kind of have a mixture of things. Well, we can't just say it's negative a half because we're taking the sine of the inverse cosine of negative a half. What you're going to do, break this up into problems, and just like other composite functions, you start at kind of the innermost part. So the innermost part is this cosine inverse of negative 1/2. What angle gives me a cosine of negative 1/2? Well, it's 2 pi over 3. So if you know that, then we're going to take the sine of 2 pi over 3. And the sine of 2 pi over 3 is the square root of 3 over 2. In some cases, inverses are not at special angles. In those cases, it's helpful to draw a triangle when they don't involve special angles. So here we're going to take the cosine of the inverse sine of 5 over 13. First thing you ought to do is draw a triangle. And we know the inverse sine of 5 over 13 means we're using the sine, so opposite over hypotenuse. The opposite is going to be 5 of this angle, and the hypotenuse is going to be 13. So we're going to find the cosine of the angle that has a sine of 5 over 13. So we draw the triangle, we label it. The only unknown part here is going to be the adjacent side, because we need the adjacent side to find the cosine. Well, we know cosine is adjacent over hypotenuse. If you use the Pythagorean theorem, or if you just remember that this is a 5, 12, 13 triangle, that's a Pythagorean triplet, the adjacent side is going to be 12. Therefore, the cosine is adjacent over hypotenuse, it's 12 over 13. So the answer to this problem is 12 over 13. Let's look at another composition example, sine inverse of the sine of 2 pi over 3. You may look at this and go, oh yeah, that's 2 pi over 3. Well, there's a problem with that. The problem is 2 pi over 3 isn't the restricted domain of the sine function that we use for the inverse sine. It's not in the domain. So you have to be careful with problems where the input value is outside the restricted domain of the trig function that we're using. Solve this from the inside out. So the sine of 2 pi over 3, that's going to be the square root of 3 over 2. So we'll take the inverse sine of the square root of 3 over 2, and that gives us pi over 3, which is our actual answer to this problem. Let's look at some application problems that involve this. Here's a pilot, and she's in her airplane 7.5 kilometers above the ground, and she's 200 kilometers along the ground from the airport. At what angle should her descent be to fly directly to the airport? So the first thing you ought to try to do in a problem like this, and it is again to draw a right triangle. Here's the plane, 7.5 kilometers up in the sky. It is 200 kilometers on the ground to the airport, and we want to find that angle the pilot needs to travel at. Now, you may be wondering, well, what does this angle have to do with the angle of the airplane? Well, another line up here, this becomes a transversal if you remember from geometry, so the angle of her descent is going to be the same as this angle, theta. We label the triangle opposite and adjacent sides. We're going to need to use a ratio that involves opposite and adjacent. Well, what is that? It's tangent. So the tangent of theta is equal to 7.5 over 200. So to solve for theta, we're going to take the inverse. Theta, this as theta, is the inverse tangent of 7.5 over 200. When you solve that, using your calculator, if you're in radians mode, you're going to get 0.0375 radians. In degree mode, that's 2.15 degrees. So the pilot would need to descend at that angle to be able to get to the airport directly. Another application. You are tying down a 4.3 meter fruit tree with a 6 meter guy wire. At what angle will the wire need to be tied to the ground? Again, draw a picture. This fruit tree is 4.3 meters tall. Your wire is 6 meters in length. So we've got opposite and hypotenuse. We're going to need to use sine to be able to find that angle. Well, the sine of theta is equal to 4.3 over 6. To be able to solve for theta, we're going to use the inverse. Theta is the inverse sine of 4.3 over 6, opposite over hypotenuse. When you solve for that, you're going to get 0.6218 radians, or approximately 35.6 degrees. So the fruit tree will need to be tied to the ground at 35.6 degrees. We've learned some of the applications of inverse trigonometric functions.